Hello all. I am Professor Archana Guruvali, working as an assistant professor in computer department. In this video, we are going to see the topic deadlock avoidance in operating system. We will start with the deadlock avoidance. So deadlock avoidance is basically the way to avoid the deadlock from occurring the deadlock in the systems. So in deadlock avoidance algorithms, again, there are two variations are there whenever there is a single instance of a resource type or when there are the multiple instances of resources are in the systems. So if only a single instance of each resource types are we are going to use in the system, then we can use a resource allocation graph, or if there is a multiple instances of a resource type, then in that case we can make use of the banker's algorithm. Okay, we'll go through both of these two topics. So, first of all, we will start with if there is a single instance of each resource type. So we'll continue with the resource allocation graph. As we know that resource allocation graph consists of the processes and resources as well as the request age, assignment age. These all the things are there into the resource allocation graph. But when we are looking at the resource allocation graph from the viewpoint of deadlock avoidance algorithm, so there is one more age we want to add here in this particular graph. One more age gets added here, and that age is called as claim age. That age is called as claim age. That is from process or thread to resource. Thread I to resource RJ. Indicated that process TJ may request resource RJ represented by a dash line. Because what we are saying, the process TJ may request resource RJ. There is not surety. It may request. So we are representing that particular request by a dash line. And that age is called as a claim age. That age is called as claim age. So this claim age converts to the request age when a thread requests a resource actually. This claim age converts to the request age when a thread requests a resource actually. Then a request age gets converted to the assignment age when a resource is allocated to the thread. When a resource is allocated to the particular thread, that request age will get converted into the assignment age. And when a resource is done with the particular resource, or when a resource is released by a particular thread, then the assignment age reconverted to a claim age, reconverts to a claim age. So resources must be claimed a prior in the system. So whatever the resources a process or thread may require, that has to be claimed in advance in the system. That has to be claimed in prior. Now we will see one example of here resource allocation graph. You can see here the resource allocation graph. Two processes are there, T1 and T2, or threads we can say T1 and T2, two processes or threads are there, and two resources are there, R1 and R2. Whereas the R1 is held by the T1, yes, this is the assignment age, and R2, R1 is requested by T2. So T2 is requesting R1, so this is the request age. And you can see that resource R2, both the processes or both the threads T1 and T2 may request the resource R2. So whenever I'm saying may request the resource R2, it means what? There is not surety. So there is a claim age. So here you can see that the claim age is given there from the process T1 to resource R2 as well as from the process T2 to resource R2. Claim age is given so that the processes T1 and T2 may claim the resource R2, and that is represented by a dash line that is called as a claim age. Now, when this claim age gets converted into the request age or assignment age, and if this particular resource allocation graph forms a cycle, then there will be a chances of deadlock. You can see that. So you can see here in this particular graph, the unsafe state in resource allocation graph. Unsafe state in resource allocation graph. So for unsafe state, there are the chances of deadlock. If the system is in the safe state, means it is completely safe. If the system is in the unsafe state, means there are the chance the system may lead to the deadlock in that case. Why there is this particular resource allocation graph is in the unsafe state? Because you can see here that this particular request claim age, the previous slide it was a claim age. Now this claim age gets converted into the assignment age. Resource R2 gets assigned to the process T2. and there is one more claim age is here. So this whole is forming a cycle. So this is the unsafe state in the resource allocation graph. Okay. So resource allocation graph algorithm is what? Suppose that any thread or any process request a resource RG of any type. The request can be granted only if the request can be granted the request whenever any process or any thread requesting some resource, that request can be granted only if converting the request age to an assignment age does not result in the formation of the cycle in the resource allocation graph. Then only the particular request can be granted. It if the request age gets converted into the assignment age and it will form a cycle in the graph, then that request will not be granted. So that is the resource allocation graph algorithm. So basically grant the resource only if it is putting the system in the safe state. If granting the resources to the system, putting the system in the unsafe state, don't grant those resources to this particular process. That is in a short. Now the banker's algorithm. So when to use the banker's algorithm? When there are the multiple instances of the resources, we cannot use the resource allocation graph because resource allocation graph can exhibit only a single instance. So better way to go for the banker's algorithm for efficient usage of the avoidance algorithm. Okay. So in banker's algorithm, we will be using it for the multiple instances of the resources where each thread or each process, whichever threads or processes are there in the system, must a prior claim its maximum usage of all the resource types. Must declare its maximum usage of all the resource types. Okay, that is the main requirement of the banker's algorithm. Then second one, when a thread requests a resource, it may have to wait. Obviously, when a thread requests a resource, it may have to wait if that particular resource may not be available, or if by allocating that resource, it is putting the system into the unsafe state. So the system cannot grant the resource. So the requesting thread have to wait. When a thread gets all its resources, when a thread or process gets all its resources, then it must return these all the resources. Then it must return these all the resources in a finite amount of time. Means the process cannot hold the resources for infinite time because there are many other processes are waiting for those resources. So suppose any process has got all the resources, it has to execute immediately, finish up all its work and release all the resources because the n number of other threads are waiting for all those resources and then they can also get executed. So every process must return the resources in a finite amount of time. So these are some requirements of the banker's algorithm. Now, to implement the banker's algorithm, we need to have some data structure. To implement the banker's algorithm, we need to have some data structure. So data structure for the banker's algorithm, you can see it here on the slide. Let's suppose n is the number of processes, n is the vector, that is the number of processes, and m is the number of resource type. So the following data structure will be required. First one is available. It is a vector of length m. If available of j is equals to k, means what? There are k instances of resource type rj available. Means there are k instances of resource type rj available in the system. Then next data structure, that is a max. Max is a matrix of n by m. N is the number of processes, m is the number of resources. If max of ij is equals to k, means what? The process I, Ti, may request at most k instances of resource type rj. May request k more instances of resource type rj. That is a maximum matrix. That indicates the maximum demand of every process for each resource type. What it indicates? Maximum demand of every process for each resource type. The next one is the allocation. Allocation is again the matrix of n by m. If allocation of ij is equals to k, it means what? Process ti or thread ti is currently allocated k instances of type of resource rj. So allocation matrix gives the current allocation of all the processes for all the different resource types. Then need matrix. Need matrix is again the n by m matrix. If need of ij is equals to k, means what? the process Ti may need k more instances of Rj to complete its task. This need matrix we need to calculate. How we calculate? By max of Ij minus allocation of Ij. So if we do the maximum minus allocation, we'll get the need matrix. So maximum demand of the process minus allocated matrix of the particular process. If we subtract it, you will get the need matrix. Okay. So these data structures we require for implementation of the Ranker's algorithm. Along with this data structure, Ranker's algorithms implement two sub-algorithms along with this. The first one is a safety algorithm and second one is a resource request algorithm for particular process. Okay, we'll see both of these algorithms. First one is a safety algorithm. Safety algorithm is to check whether the system is in a safe state or not. Safety algorithm is to check whether the system is in a safe state or not. Okay. So here we'll see the algorithm. Let work and finish be the vectors of length m and n respectively. So initialize work is equals to available resources and finish of I is equals to false for all the processes from 0 to n minus 1. Find an I such that both finish of I is equals to false when the finish status of that particular process is false and need of that process is less than equals to work or available. If need is less than equals to work or available, then we'll go to, if both of these conditions true, then we'll go to the third stage. But if no such I exists, then we'll go to the step 4. If finish of I is equals to true for all the I, then the system is in the safe state. Means all the processes are executed. But if it is not the case, means if these both the conditions are true, it will follow the sequential thing. That is third step, work is equals to work plus allocation. So we basically what we are doing, if both of these conditions are true in the step 2, means what? The process, we are going to execute that process. So after we are pretending to execute that process, so here what we are doing, we are after execution, we are adding all the allocated, so we're releasing all the allocated resources and adding it to the work vector. So updating the work vector over here, work is equals to work plus allocation of I. And finish of I, that is I process का जो भी finish होगा, that we are making it as a true. And then go to the step 2 for the next process in the loop. Okay, once we are done with it, if in the fourth step, we check if finish of I is equals to true for all the I, then the system is in the safe state. If finish of I is not equals to true for all the processes, or if it is false for any one of the processes in the set of processes in the system, then the system is not in the safe state, it will be in the unsafe state. So this algorithm is used to check the safety of the system, to check whether the particular system is in the safe state or the unsafe state. It will print accordingly based on the given allocation and the availability of the resources. Okay, so this is the safety algorithm. Now we'll see the second algorithm, that is the resource request algorithm for the process Pi. So here, before allocating this algorithm is what basically, so whenever the resource, any particular process requesting some resources, any particular process requesting some resources. So before allocating the resources to the system first execute this algorithm to check whether the allocation of these resources to the process Pi will leave the system in a safe state. If it will leave the system in a safe state, then this particular algorithm will grant the allocation of the particular resources to the process. If the system will not be in the safe state, it will say that this particular resources cannot be granted to the process Pi. So that is the basic use of this particular algorithm. So we'll go through the algorithm here once. So request of I is equals to request vector for process Ti. If request of I of j is equals to k, means what? Process Ti wants k instances of resource type Rj. So process Ti is basically making the request for resource type Rj for k instances. So once the request has been made, what we need to do, we need to run this algorithm. And this algorithm will, what it will do, it will go through these all the steps. First step is what? If request of ith process is less than equal to need of that ith process. If request of ith process is less than equal to need of that process, yes, it is correct one. Then go to step 2. But if it is not the case, then otherwise raise the error condition that since the process has exceeded its maximum claim, because in banker's algorithm, the process has to declare its maximum usage of resources. And if the process is requesting on top of this maximum claim, then it is a error condition. So that's why this condition, if request of I is less than equals to need of I, if this is true, it will go to the step. In step 2, what we are doing, we are checking if request of I less than equals to available. If request of I process is less than equals to other available hai, then we can allocate the resources. So go to step 3. Otherwise, TI has to wait since the resources are not available in the system currently. So in the step 3, what we are doing, we are pretending to allocate the resources to the process TI by modifying the state as follows. We are just pretending here by modifying the state as follows. So what state we are modifying? We are modifying the available, we are modifying the allocation, and we are modifying the need. And then we are again checking. Okay, first of all, we'll modify. So available is equals to available minus request, because we are granting the request. So available में से minus हो जाएगा. So available is equals to available minus request of I. Then allocation of I is equals to allocation of I plus request of I, because requested, whatever resources are requested, that are also allocated. So add it to the allocation matrix. Then need of I is equals to need of I minus request of I. Need will be reduced again. So modifying these states, after modifying these states, if this particular states leave the system in a safe state, then the resources are allocated to the TI. So here you can see, if safe, the resources are allocated to the process TI. If unsafe, TI must wait, and the old resource allocation state is restored. And the old resource allocation state is restored. Old resource allocation state means the state before this particular modification. State before this modification, what was there, that will be restored here. Okay, so that is the resource request algorithm for any process. Whenever any process is requesting the resources, it has to go through this particular algorithm. And safety algorithm is there to check whether the system is in safe state or unsafe state at any time. So these two sub algorithms are there into the banker's algorithm along with the 4 data structures that we have seen. Now we'll see one example of the banker's algorithm. So you can see here, there are the 5 processes or threads are there, T0 to T4, and 3 resource types are given. A, which is having the 10 instances, B, which is having the 5 instances, and resource type C, which is having the 7 instances. So snapshot of particular system at time T0. So these are the processes or threads. This is the current allocation matrix, maximum matrix, and available vector. This is given. Now we need, based on this particular snapshot or this particular example, what we need to do next is we need to calculate the need matrix. We need to calculate the need matrix. So need matrix, how to calculate? Max minus allocation, you will get the need matrix. So based on that, here we have calculated, you can see that. So the content of matrix need is defined as max minus allocation. So after this subtraction, you can see the need matrix contents are here. Need matrix contents are given over here, and this is the available. Available is copied from this previous slide as it is, that is a 332. So this is the available. Now you need to compare this need with the available, and you need to check which process gets executed first. So you need to basically here define the safe sequence of the processes or the threads which are available in the system. So you can see how many resources are available, 332. Need of ABC is what? 743. Can we execute? No, it is greater than the available. 122. Can we execute? Yes, we can execute it because this T1 need is less than equals to available. So we can execute T1. So that is the first step sequence. The first process in the step sequence will be the T1. Okay. Then after the T1 gets executed, what we will do? We'll update the work. That is the available will get updated. So whatever the allocation of the process T1 will get added to this particular available, and the available gets updated. And then we'll again check here and accordingly define the step sequence. So the step sequence for this system is T1, T3, T4, T2, and T0, which satisfies the safety criteria. So based on using the safety algorithm, here we have found the safe sequence. So safe sequence, if the safe sequence presents, means what? The system is in the safe state. Okay. Now, suppose with the same example, if one of the process requests some resources. Suppose, for example, P1 is requesting the resources 102. P1 is requesting the resource 102. So what we need to check? We need to check that request is less than equals to need of that particular process. If it is so, then check request is less than equals to available. So here we are checking. Request is less than equals to available. Request is what? 102. Available is what? 332. You can see here. The available is 332. Okay, so that what we are checking here. So it is less than equals to that. So the condition is true and it will leave the system into the valid state, means allocation of those resources may put the system in a safe state only. So we can allocate the resources. So after allocating the resources to the particular these resources to the process P1, so the newly allocation need and available vector are like this given over here. You can see after allocation of 102 resources to the process P1. So updated matrix and updated available vector is 230. It is given like this. Then again, you can execute the safety algorithm on this particular system, which shows that the sequence T1, T3, T4, T0, and T2 satisfies the safety criteria. So this T1, T3, T4, T0, T2, what is that? This is the safe sequence. So if safe sequence is present, means what? The system is in the safe state. So after every resource request algorithm, you need to again run the safety algorithm. So that is about the banker's algorithm. So I hope you understood the banker's algorithm. Thank you for patient listening. Let's see you in the next video.